Consider the initial value problem. Y prime is equals to minus ty subject to the initial condition y naught is equals to 1. I'm going to use Taylor series method with a step size h equals to 0.1 to approximate y at 0.2. Then I'm going to calculate the absolute error for this method. So we are given that first order ODE there. So I'll start by looking at the first question there, using Taylor series method to approximate y at 0.2. So using a Taylor series method, yn plus 1 is equals to yn plus y prime n multiplied by h plus 1 divided by 2 factorial multiplied by y prime prime n multiplied by h squared plus 1 divided by 3 factorial multiplied by y prime prime n multiplied by h cubed plus 1 divided by 4 factorial of the fourth derivative of yn multiplied by h to the power 4. And the h here is the step size. So we are given our initial condition. It's y naught is equals to 1. So we would have that our y naught there is equals to 1. So I can just illustrate using a number line what we are having. We'll be starting at a point 0, then moving with our step size of 0.1 the h, so we'll be moving to the point 0.1. Then we make another step, then go on to step 2 there. We will be having t equals to 0.2, which is what we want to evaluate y at. So when we start, we are at y naught, and then y1, then the value that we want is at y2, which corresponds to t equals to 0.2. Now in our formula here, what we're having derivatives of y here, of the y prime, the third derivative, and the fourth derivative. So for us to obtain y prime prime, we differentiate this y prime with respect to t. But what we see there is minus t times y there is a product of two functions of since y is a function of t. So for us to differentiate minus ty, we would have to use the product rule. If you still go for the product rule, the derivative of u v is equals to u prime v plus u of v prime. So we go on and use the product rule. So in this case, we will choose that our u is equals to the minus t, and the derivative of u with respect to t, it gives us a minus 1. Then for our v is the y, then the derivative of v with respect to y, which is v prime, will just be the derivative of y, which is y prime. So substitute what we have just obtained into the formula for the product rule there, then we would obtain that y prime prime is equals to minus y minus t times y prime. But we also have the value of y prime here is minus ty, so we can substitute it here, so that would have minus y minus t times minus ty, and that will simplify to minus y plus t squared multiplied by y. So that's our y prime prime. We now go on and evaluate y prime prime prime, the third derivative there. So for the third derivative, what we start by doing is we differentiate this one here, minus y. The derivative of minus y gives us a minus y prime. But now for the derivative on this part here, t squared multiplied by y, that's a product of two functions of t there. So what we'd have to do is we have to use the product rule again. So in this case, we'll choose that our u is equals to the t squared, then differentiate u with respect to t, and we get 2t. And then for our v, it will be the y, then the v prime, it will be y prime. And then use the formula for the product rule here, and our result will give us 2t multiplied by y plus t squared multiplied by y prime. So that's our third derivative there, but we are having these parts here, y prime. We know that our y prime is minus ty from this equation here. So that will simplify to 3ty minus t cubed multiplied by y. So that's the third derivative. We now need to find the fourth derivative. So for the fourth derivative, we are differentiating this with respect to t, so that we obtain our fourth derivative. But this part here is a product, so we'd have to use the product rule. So for the product rule there, we would use our u is equals to 3t. The derivative of u is equals to 3. Our v is equals to y, and then we have v prime is equals to y prime. So we plug it in into the formula for our product rule, then we would have the fourth derivative there is equals to 3y plus 3t times y prime. That's the first part. But we also need to look at this second part again. It's a product, so we'd have to use the product rule again so that we obtain our u is equals to minus t cubed and our u prime, differentiate this with respect to t and we get minus 3t squared. And we have that our v is equals to y, that the derivative of v, which is v prime, will be equals to y prime. Substitute into the formula for the product rule, then we would have our result for the second part is minus 3t squared multiplied by y minus 3 minus t cubed multiplied by y prime. And we substitute the value of the y prime, which we are saying is minus ty here, so that our fourth derivative becomes 3y minus 6t squared y plus t to the power 4y. So that's our fourth derivative there. Now for us to obtain y1, which is y at the point t equals to 0.1, using the formula for Taylor series here, we substitute n equals to 0, so that we would have y1 is equals to y naught plus y prime naught h plus 1 divided by 2 factorial plus y prime prime naught h squared plus 1 divided by 3 factorial multiplied by y prime prime naught h cubed, then plus that part where we have the fourth derivative, and we go on and so on. But in this case, we are saying that our step size h is equals to 0.1, so I can just write it here, h equals to 0.1. So we now substitute the value of y naught. The value of y naught, we have it here, is a 1. So this one is equals to a 1. That's the first part. Now for the second part, this one, y prime naught. Y prime naught, we get it from this equation, y prime minus t times y. So that will give us a y prime naught is equals to minus 0 times y0, because we are saying at y naught here we are saying t equals to 0, so that's why you are having a 0 here. 0 times y naught, 0 times y naught gives us a 0, so it will be plus a 0. Then we go on to this part where we have y prime prime naught. For y prime prime naught, we get it from this equation here. So that what we would have there for the y prime prime naught, it will be y prime prime is equals to minus y naught plus 0 squared times y naught, because we are evaluating at t equals to 0. And this simplifies to minus y naught, because this part with a 0 gives us a 0. So what would remain there with is a minus 1. So we'll write plus a half multiplied by minus 1 times 0.1 squared. I substituted the value for the h there, which is 0.1. Then we move on to the next part, where we are now looking at this third derivative, y naught. We substitute it here. So we have that the third derivative at y naught is equals to 3 times 0 multiplied by y naught minus 0 cubed times y naught. We are multiplying by zeros there, so it will simplify to 0. So for this part where we have the third derivative, we would be having 1 over 3 factorial multiplied by 0 multiplied by 0.1 cubed. And then we move on to the next part where we have this fourth derivative. So where we have the fourth derivative, we would have the fourth derivative at y naught is equals to 3 times y naught minus 6 times 0 squared times y naught plus 0 to the power 4 times y naught. Just because at y naught we are looking at t equals to 0, and that will simplify to a 3. So we would have 1 divided by 4 factorial times 3, then times 0.1 to the power 4. So that's how we obtain our y1. And when we just simplify those values, what we get there is y1 is equals to 0.9950 after rounding that value there. So that's our value for y1, and we will use it to obtain the y2. So for us to get y2, we substitute n equals to 1 in this equation here, so that we would have y2 is equal to y1 plus y prime 1h plus 1 divided by 2 factorial multiplied by the second derivative multiplied by h squared plus 1 divided by 3 factorial multiplied by the third derivative plus h squared, then plus the term where we have the fourth derivative there. So for the first part, it just simplifies to the y1. But for the second part, we are saying that our h is equals to 0.1, so I can just write it as 0.1 multiplied by y prime 1, and then plus a half, then multiplied by y prime 1 multiplied by 0.1 squared. And then substitute again the value of the h there, would have 1 divided by 3 factorial times the third derivative times 0.1 cubed, then plus 1 divided by 4 factorial multiplied by the fourth derivative multiplied by 0.1 to the power of 4. But on this part where we are having y1 prime, y1 prime, we get it from this equation. So we have y1 prime is equals to minus t times y1. And for y prime prime 1, we get it from this equation, and it will be y prime prime 1 is equals to minus y1 plus t squared multiplied by y1. And for the third derivative at y1, it will give us 3t multiplied by y1 minus t cubed multiplied by y1. And for the fourth derivative, we use this equation here. So we'd have 3y1 minus 6 times t squared y1 plus t to the power of 4 multiplied by y1. So in these equations that I've highlighted here, we can substitute out the value of the t. At y1, the t is 0.1. And we are using the value of y1 equals to 0.9950. So when we do that, our expression here will simplify to 1 minus 0.01 minus 0.00495 minus 0.0005 minus 0.00001 multiplied by y1. And when we simplify that, it will give us that our y2 is equals to 0.9802. So what we are having here is, using Taylor's method, the value of y at 0.2 is approximately equal to 0.9802. So what we have found there is the approximate value of that differential equation at 0.2. So we now go on and calculate the absolute error. For the absolute error, if you still recall, we said it is the absolute value of the difference between the true value and the approximate value. But for us to get the true value, we need to find the analytic solution of this differential equation. So I will write the differential equation in full there. That's the derivative of y with respect to t, which is equals to minus t times y. We see that this is a separable differential equation. Put the variables y on one side, variables t on the other side, then go on and integrate. And what we would obtain there is the integral of 1 over y with respect to y is equals to the integral of minus t with respect to t. And when we integrate, the result that we get is ln of the absolute value of y is equals to minus t squared divided by 2 plus a constant of integration c. And we can make y subject of the formula, take exponents on both sides, so that we would have there our y is equals to a constant c1 multiplied by exponent of minus t squared divided by 2. And this constant c1, I obtained it by taking the exponent of c, because it will give us exponent of c multiplied by the exponent of minus t squared over 2. So the exponent of c is the one that I wrote as the c1 here. But for us to obtain the value of that c1, we use this initial condition that we have. So we substitute t equals to 0 into this equation. So what would have 1 is equals to c1 multiplied by exponent of 0, which will give us c1 is equals to 1. So substitute c1 equals to 1 into this equation, then we have y is equals to exponent of minus t squared divided by 2. Now to evaluate the value of y at t equals 0.2, we substitute t equals to 0.2 here, so that we have y at 0.2 is equals to exponent of minus 0.02. Just suppose 0.2 multiplied by 0.2 gives us a 0.04, then divided by 2, which gives us the 0.02. So for our absolute error, it will be the absolute value of exponent of minus 0.02 minus 0.9802. And that value will be approximately equal to 0.000001. So that's the absolute error that we are having there. What we are seeing there, the value there of the error is very small.